So in yesterday's lecture one, I did one variable calculus. What happens at an optimal point? If you have a minima or maxima, then your derivative must be zero, and there is so that was what I mentioned as Fermat's theorem. And Weierstrass theorem gave you the existence. If the function is continuous on a compact set, then it attains its maximum and minimum. So in lecture one, pretty much we saw the one variable and several variables, and then without constraint was the simplest one. Then we saw with constraints, and there we saw how Lagrange's multiplier rule helped us to solve the problem. It was basically to introduce one extra variable of the Lagrange multiplier, depending on the number of constraints. If you had only one constraint, you add one multiplied by one Lagrange multiplier, and then you differentiate with respect to all the variables x and lambda, and then you try to solve for the optimal point. Now, if the constraint may be equality constraint or inequality constraints, and the inequality constraint then could be linear constraints, which was the famous linear programming problem, and or it could be convex constraints, in which case also you are able to write down a modified version of Lagrange multiplier rule, which is known in this case as Karush-Kuhn-Tucker or KKT conditions. And then using these KKT conditions, you may be able to solve. By hand, I'm not sure, but at least by computer you may. Because as I pointed out, if you have m constraints, and each of the complementarity condition will throw up two possibilities. So you quickly raise to a 2 power m possibilities. So you have to go on eliminating the possibilities and see which will be your required optimal point. So this is amenable to numerical computation. So that is where we stopped and then came to lecture 2, which is historically it moved to infinite dimension. The calculus of variation problems took over, and I mentioned Bernoulli brothers and how the Brachistochrone problem stimulated a lot of interest. And then it led to the beginning of calculus of variations. But in this case, the problem is in the form of an integral depending on a function which is varying in some function space. So the function space is being infinite dimensional. So we have moved to infinite dimensional optimization. So what happens to Lagrange multiplier? That is what we wanted to see. And a little later, Pontryagin and Richard Bellman started looking at optimal control problem, which is of the similar nature. You can have a constraint depending on the x dot, or your constraint is going to be a differential equation. So how do we solve that? Was the question. And then there was we wanted in this case the Fermat's equation, that is you have the optimality conditions, first order conditions will be Euler-Lagrange equations, and we wanted to derive that Euler-Lagrange equations. Yeah, so the general framework will be J, which is the function, cost function, or which is to be minimized or maximized, and that is integrated from A to B, and it depends on 3 arguments: t, the running variable; x of t, x is the curve, x of t, a smooth curve, we will take it to be c1, c2, whatever; x dot of t is the derivative of that curve. So L depends on these 3 arguments, and you integrate it out, it gives you a number. So J is real valued, and you are asking what is the maximum or minimum of J under the constraints that your curve should connect point A to point B. and that is starting at little a from point capital A to reaching at t equal to b at capital B. So this is the basic formulation of the problem of calculus of variations, and we wanted to know how do we solve such a problem, in particular Brachistochrone problem also. So this space is equipped with the usual C1 norm, and then we saw, I didn't derive this, but the idea is very simple. You have to give a small perturbation to the optimal point x tilde, which is a curve now. You will change it to x tilde plus theta h and then reduce it to a function of theta. When theta is 0, you know that is going to be, the integral is going to have a minimum. And that is, then you have the whole crux of the proof lies in calculating the derivative of the integral function uh, as a function of theta, but theta will depend on x tilde and all this. So that is where chain rule will have to be used very carefully. That will give me this Euler-Lagrange equation. And yeah, the reference could be Ivan's PDE book in the chapter Calculus of Variations. Okay, so then I gave a very simple example where it is just quadratic in x dot and linear in xt, and with the endpoints at 0 and 8. Then we write down the Euler-Lagrange equation. Then I get two integration constants, little a and little b. And I want to calculate what are the values using the initial and terminal conditions. So that gives me the minimizer to be xt is equal to tq. This is a very simple toy problem. Let us see if we can apply it to Brachistochrone problem, and that is what I wanted to derive. What is the J? After some computations, we arrived at the T of U, which is the time taken to go from point A to point B, is of this form: 0 to B, square root of 1 plus u prime x square by square root of 2g into y1 minus ux. Now, what is u? We are assuming the curve to be x comma xt comma uxt. So the x coordinate is parameterized like this, and this is the y coordinate, and the points are capital A is 0, y1, and capital B is b, y2. So that is why we are integrating from 0 to b this. Now the point is we have to minimize this integral over all the C1 paths going from y1 to y2. Under the condition, it connects point capital A to point capital B. Now, yeah, I didn't give you all the computations because it was quite tricky after a point, because we ended up with u double prime into u is equal to half into 1 plus u prime square. Did anyone try to solve this problem? Okay, the hint is you can multiply by, let me see, I think you multiply by u prime. So on the left-hand side, I keep everything in terms of u prime. Okay, so it will be um, u double prime by 1 plus u prime square into u prime. But u I don't want on the left hand side, so I bring it to the right hand side. But I have, as I have multiplied everywhere by u prime, so the right hand side will be u prime by u. Now you recognize the pattern. The left hand side numerator will be the derivative of u prime square, and the denominator has 1 plus u prime square. So you can substitute and you will get some log function on the left hand side. Similarly, on the right hand side, I'll have, what do I have? U prime by u. Again, you can integrate it to get the log function, and that can be simplified. Further substitution will be needed. So that is how trigonometric functions will come in. And finally, you will get the cycloid. And so now I mentioned that was, suppose one endpoint is free, then you will have to evaluate the derivative of L with respect to the third argument x dot evaluated at that endpoint B. Otherwise, if the first initial state is free, then you will have to evaluate Lx dot at A, etc. So I gave an example, the same example with only the initial condition. So the terminal point is free, and that will lead to the condition 2x dot into 2 is 0. That helps you to solve the problem, and we find the minimizer. So then we move to the optimal control problem, and here it is very similar. J is to be minimized from over all the curves xt. L is again a function of t xt ut. Now ut is the control, and the x dot, what is x dot is evolving according to the dynamics f of t xt ut. In particular, if I had called earlier Brachistochrone problem x dot equal to u, then you see it is the same functional what we solved recently on the Brachistochrone problem. And there the initial condition was x0 was A and x capital T was B, etc. So that problem can also be put as the optimal control problem, because we are, after all, we are minimizing the time there, which can be written in terms of a differential equation by involving a U. So we call it a dynamic optimization. And a typical example is the moon landing problem. So I mentioned this is the Newton's laws, which we want to solve, so that the J of alpha of T, alpha is the thrust I explained. So we wanted to maximize the mass which is left over when we land on the moon. So that is again, you have to find what is the minimum. You have to write it in the terms of the integral, and then okay. So the control problem in general, I'll put it in the framework like this. We are looking for minimum of L of t xt ut plus g of xt subject to this differential equation with the dynamics f, and with certain mixed boundary conditions at 0 and t, and the control set of the control ut is in a non-empty convex closed subset. We always denote it by u of add. U add, which is a subset of Rn. If it is the whole of Rn, then I call it no control constraints, and that will be the easy case to work with. J is the cost functional, L is called the running cost, and G is called the terminal cost. Now we want to see how to write down whether the Lagrange multiplier idea will work here and what does it give. So I have to first find the augmented functional. So we are going to treat the differential equation as a constraint, plus the terminal conditions are also as constraints. Now the terminal conditions are imposed in RD, then I'll need a Lagrange multiplier from RD. I'll take a inner product from that Lagrange multiplier and these conditions. And if the equation is posed in Rn, I'll choose a Lagrange multiplier from Rn. So that is what is P. So the P, actually here it is also known as the adjoint vector or co-state vector, or it actually, you can view it as a Lagrange multiplier corresponding to the differential equation x dot minus f equal to 0, which we are treating as a constraint. And the beta, the first boundary condition, is multiplied by mu, which will be an RD vector. And lambda is another RD vector. That's why I have put mu transpose. So what it means is the scalar product in RD, mu comma beta. That is the scalar product. And the next one is the scalar product in RD, lambda comma gamma. The first one in the integral 0 to t is the inner product between P and x dot minus f, both are Rn vectors. So this is the Rn inner product. Okay. So I have augmented the functional, which we call J tilde. So what is the integrand? Now the integrand I denote by L tilde. L tilde is earlier one lambda naught L. Yeah, so the lambda naught is always added, as I told you, to avoid the degeneracy case. Because we simply wrote down gradient of f equal to lambda times gradient of g. Now this has to hold even when gradient g is 0. Gradient g is 0, right hand side is 0, but left hand side need not be 0. So to handle such degenerate cases, we'll keep the lambda naught multiplied by the functional, so that whenever we hit a degenerate case, we will handle the lambda naught to be 0. So that was the question yesterday, I think somebody asked. Okay. So now, yeah, there is a control Hamiltonian. Some people will introduce with negative of h, or this way I have introduced. So this will give me the optimality system to be a Hamiltonian system. So that is why it is called a control Hamiltonian. There are also other explanations. So I have taken lambda naught L minus P transpose Fxu. Now the optimality conditions. So if you formally write down what does the calculus of variations applied to J tilde gives you, that will give you d by dt of L tilde differentiated with respect to the argument x dot. All this evaluated at the optimal point x tilde minus L tilde differentiated with respect to the argument x. So that is what we have to calculate. Now that will give me, if I go back, if x dot is multiplied by P transpose. So that will give me just P, d by dt is also sitting. So I will get a P dot, okay, the derivative of P with respect to T, minus, now L tilde differentiated with respect to X, that X occurs just in what I have written as H. So I can write it as H differentiated with respect to X, the variable X. So this must be 0. And that gives me, if I expand Hx, H differentiated with respect to X, so there is a lambda naught gradient XL, all this evaluated at the optimal pair X star U star. And there is also P transpose Fxu that has to be differentiated with respect to the variable X. So that will give me PT transpose DFT X star PUT. I have used D and gradient, but they both are the same. That they both represent the Frechet derivative or total derivative of the function involved. Now that is the, again, it's a differential equation. We end up with this differential equation for P. Now transversality conditions, they are obtained through variations in the parameters. So L tilde has to be differentiated with respect to x dot and evaluated at t equal to 0. That will correspond to the I have put gradient of 1 to denote it is differentiated with respect to the first group of variable, which is x0. If it is a nabla 2, then it is differentiated with respect to the second group of variable, which is xt. So these will give you some conditions at 0 and t, and that should help you to solve the ODE P dot, and that will supply the terminal or initial conditions for P dot. So all this will be the optimality condition. So now we are ready to mention Pontryagin principle. So there was one thing I forgot to mention. So I have added U. I have not differentiated with respect to U. Now that will appear in the Pontryagin principle, because the original H not only depended on X, it will also depended on U. So that will give you this minimum quality, minimum principle or maximum, the way you write H. If you had called H as with a negative sign, you would have got a maximum principle. Okay. Under usual smoothness assumption, if X star, U star are optimal processes, then there exists lambda not greater than or equal to 0 and lambda greater than or equal to 0. Where was this lambda? I forget.
Excuse me, can
Yeah,
you just show me the previous slide?
yeah.
And before this, one more.
Before this, yeah.
Is it possible that this L
Uh,
tilde, that L depends
uh,
on x dot as well? Because you are taking derivative with respect to x dot.
yeah, in this, yeah, L tilde depends on X dot. The original L, I have not taken it depending on X dot. It was only on all the X dot is pushed to the differential equation. I have put only the control.
Mhm.
Whereas, I understand your question. Whereas in the calculus of variation problem, I had Lx and x dot.
No,
The
because
third
you have
variable was also there, right?
no. The reason I'm asking is the derivative with
Yeah,
x dot is
yeah.
there. That's
So that's why I have said
here.
formally, because it is analog of calculus of variations.
Yeah,
There,
same thing
what
in
was
mechanics. You have classical mechanics similar.
so the L tilde I'm applying to, not to L. L tilde has still x dot dependence.
Okay.
So I'm applying it to the J tilde is now with this L tilde.
Okay.
That is why I don't have to allow there.
Okay.
Okay. So the L tilde still has x dot dependence. So I can apply the. This was the J tilde, right? J tilde is the augmented stuff. So I have the original J plus some more terms. So that is the integrand is this L tilde, for which I am applying the partial. Now the L tilde, like you pointed out, it depends on x dot, t, and also u. I have not differentiated with respect to u, but that will come in Pontryagin. So this is what is the calculus of variations Euler-Lagrange equation. So that gives me for one Lagrange multiplier or adjoint vector P dot. We'll see why it is called the adjoint vector soon. Okay, so then I think this lambda and mu are vectors. So I don't know, this lambda greater than or equal to, I did something. Okay, sorry.
So
Where
there
did
is a
it go?
question in the
Yeah,
question
yeah,
list.
go ahead.
So the question is, ma'am, what does P denote here? Is it also the Lagrange multiplier?
Yeah,
Can-
it has several interpretations.
Hmm.
It is a Lagrange multiplier. For if you treat the differential equation as a constraint, so you are multiplying it by the Lagrange multiplier P. So P is the Lagrange multiplier, but it has, in control theory, it has, we will see, we will call it adjoint vector. Because when I take up the PD optimization also, you will see P will solve the, here also, in fact, in the ODE case also, P will solve a differential equation, which will turn out to be the adjoint problem to the original equation for X. So we can also call it as, view it as an adjoint vector. So, or they call it state vector, co-state vector. So there are many terminologies, but it is the Lagrange multiplier, which if you treat the differential equation as a constraint. Now, what I was coming to was Pontryagin principle. Then there exists lambda greater than or equal to 0, and I don't think this lambda greater than 0 I wanted to correct, but it is, yeah. Now I think it will, I don't know how to, yeah. Okay. Lambda and mu are all in RD. So lambda greater than or equal to 0 doesn't make sense. So lambda naught must be greater than or equal to 0. That is the one. And lambda and mu and RD, they exist. And a vector function P dot, the vector function P will be in Rn, satisfying the adjoint equation, together with the boundary conditions given by the transversality relation, which I mentioned in the previous slide. So P dot satisfies the, in ODE case, it is the same equation, P dot equal to something. So that is the adjoint problem we'll call. And with the boundary condition given by the, I having trouble with the writing. Okay. And the last one you will get by minimizing with respect to the variable u, which I didn't mention earlier. So if you minimize with respect to u, you will get the minimum of the Hamiltonian H will be attained at x star, u star, and pt. That u star will be the minimal point. So that is the Pontryagin maximum principle or minimum principle, the way you write the H. Now, the thing is, how do we use it? The using is, we'll try to see in a simple example. So I've taken all linear equation once again. So I have a cost functional j of x dot u dot. Let's say it is 3u minus 2x. So it is actually 3u dot u of t minus 2x of t dt. Okay. So that is why I have put u dot x dot. So the u is really a function of t and x is a function of t. And you integrate the whole thing with respect to t from 0 to 2. And what is the constraint? The differential equation is x dot of t is equal to xt plus ut. So t is the variable for the differential equation. When t equal to 0, I have initial condition 4 and the ut is constrained to lie in the interval 0, 2. Now we have to solve this. We have to minimize this integral function. So how do we do that? So first thing to write down, let me recall what was our H. If you recall the H was lambda naught. The L was the integrand in the original J minus P transpose Fx. So I will go here. And so I get lambda naught into the integrand for j was 3u minus 2x minus, and then I have to write what was in the p into the dynamics x plus u. So this is my H, and now I have from the previous theorem, I have this systems. I have to solve them simultaneously. X dot is x plus u and p dot is hx. That's what we found out. H has to be differentiated with respect to x. So that gives me minus 2 lambda naught minus p. So I have this equation for the state x and equation for the adjoint vector p. So these are coupled actually. So they will have to be solved. But actually in this case, p can be solved independently. And then I can put it in to calculate u. But how to find out u? See, p can be solved, but I don't know how to find u. So there we have to use the fact that H assumes its minimum at the optimal value U star. Now if you look at H, how do I find the minimum for H? What is the minimum value of U, you can ask. So this is all linear in U, so it's easy. So what you could do is, I write it as U multiplied by something and then the rest. U, if you see, U is multiplied by 3 lambda naught. I'm going to drop the lambda naught finally as 1. 3 lambda naught and minus p. This is the u which is multiplied, and what is remaining, I have to plug them together, which is, I think, minus 2 lambda naught x minus px. So if I have to minimize this quantity with respect to u, so you can see that the last terms, they don't matter at all. They are independent of u. So what matters is only the first term, which is involving u. Now u is multiplied by a coefficient 3 lambda naught minus p. So that sign of that coefficient will affect us whether we'll get, and what I know is h has to attain its minimum. And the values allowed for u is only lie between 0 to 2. Now, if 3 lambda naught minus p is, let us say, it is positive, then you can argue that the minimum value will be attained if I choose u to be what should I choose u? U has values in 0, 2. And if the coefficient, suppose the coefficient is positive, okay? So if I choose u to be 2, it will be very large because the coefficient is already positive. But I have to minimize because the best optimal u is when h has the minimum. So if I have to minimize, the minimum value will be when u is 0. So that is the way we argue to get the optimal value of u. Similarly, if this is negative, then the minimum value will be, if I keep u anything highest value, then also it will be the lowest negative value. So u can take the value 2. So this is the way we can argue. So I go to the next slide where I have taken lambda naught to be 1 as we always do. So my Hamiltonian is u into 3 minus p minus, did I write correctly? 3 minus p, yes, minus 2 plus p into x. Now the 2 plus p into x it's not involving u. So I have to only concentrate on this. What value of u will make h to be the minimum? Because that is how we will guess the value of u star. So I guess it to be 2 if the coefficient is negative or 0, or I guess it to be 0 if the coefficient is strictly positive. In either case, I will have to solve the p dot equation with the condition P2, transversality condition. Did I write down? I think I forgot to write down. Transversality condition will be the differentiated at the value 2, that will give me PT naught, P2 is 0, and that will give me PT, if you integrate this ordinary differential equation with the terminal condition P2 equal to 0, I end up with this solution. So I have found PT. Now it depends, I have to find out when 3 minus P changes sign, because that will determine my U. The U is going to take only two values. The value is either 2 or 0. But the value, it changes exactly when P equal to 3. So what we have to do is we have to find out T naught when PT naught is 3, and below that you will have one value, above that you will have another value. So I have calculated what is the T naught. T naught comes out to be that 2 minus something. I may not need this, but I need only the value of P. So if you go on, the optimal control in 0 T naught was ut equal to 2. That's what we found out. Now you plug in this value and find the optimal trajectory in 0 T naught. X dot will be x plus 2. It was x plus u. Now we decided u is 2 because that will make the Hamiltonian the smallest. So x plus 2 and x0 is 4, and this gives me the solution to be the optimal trajectory is this. Now similarly, I have to do T naught to 2, optimal control u is 0, and then I integrate it, and that will give me this solution. So finally, I have we have found out the optimal control as a constant in 0 T naught as 2 and another constant in T naught to 2 as 0. And then that also gives me the optimal trajectory. So this is the way we use Pontryagin maximum principle. In big problems, we may not be able to calculate the minimum of h so simply. Here it was too trivial to calculate, but we can numerically compute and we can use the value of u and go back and forth to solve p and u. So it's more amenable to computer calculations. Okay, so what was Bellman's approach? So here I want to recall that it is sometimes easier to solve a problem by embedding it in a larger class of problems.
There is a
We
question.
already,
May
yeah,
I
please
ask?
go ahead. Yeah.
Saurabh is asking, under what conditions, assumptions can we guarantee that a general nonlinear optimal control problem with inequality constraints, path constraints, will have a unique solution? Please give some references that might have such a result.
Yeah, that usually the result I know of for if everything is convex, and under convexity assumptions, one can expect not only the solution to the inequality constraint problem, it could also unique. So the references, I think I have put the reference in the end. I'll come to that. One of them, I don't recollect, but anyway, I'll give you the reference at the, but generally it is the convexity assumptions. Anything else?
No, that was the only question.
Okay. Okay, so yeah, I was telling you that if sometimes it's easier to solve a problem by embedding it in a larger class of problem. So what we try to do, if you remember, even in Lagrange method, we try to add one more variable. We embedded in a bigger problem with having n plus 1 variables, and then it was easier to solve. It's a similar story here. You want to embed it in a larger class of problems. So what is the new variable that we are going to add? So we embed it in a maximize. So yeah, let me fix it. Here I am following Ivan's lecture notes. He prefers always maximization. So I have to recall it is going to be a maximization problem. And j of xt x dot u dot, you instead of 0, you vary the lower end point for any time t, and the x also is any point as the starting point. So that is why j has a suffix x comma t. X can be any Rn vector, which could be the starting point for your differential equation. And the t can be any starting point above 0 or above, below t, capital T. So we have got j, it has more dependence. It depends on x and t. Now you could ask, if I do the minimization problem, I'm going to get the maximum value of j, but that function will depend on x and t because we carry this dependence, the t and x. Then we could ask, how will the maximum value of j that you find will vary with respect to x and t? Now that gives some results, and that one way of approaching the optimal control problem. So we see that j can be original j can be embedded in a family of problems if I vary x in Rn and t in 0 to t. Now I can define my value function. What is the value function? That is the maximum value of j for each xt. So this value function will depend on the variables x as well as t. And so supremum is taken over all the controls u in admissible controls u, and the j depends on x dot and u dot, and then you want to talk about the supremum value, which is now a function of x and t. And if little t equal to capital T, obviously, sorry, how do I? Okay, I don't see how to, yeah, here. Okay. Yeah. Okay, so this function, we will take the value g at when t equal to capital T. That is because when little t becomes capital T, the integral is 0. You are left with only the terminal cost g. So that will be the value of the function at capital T. So I know it has the terminal value, but does it satisfy some equation? That you can ask. So for simplicity, we can assume the set of values capital A, the control u dot, to be compact. That will make it easier to prove many things. So we'll assume the range of the control set, control u, is going to be compact. And we can show that this value function satisfies a partial differential equation. And that is called Hamilton-Jacobi-Bellman equation. So if you assume the value function is C1, then the value function satisfies the nonlinear partial differential equation, which is dV by dt plus maximum of these two parts, which is the dynamics F in a product gradient of V. So this is the first derivative, partial derivative of V with respect to X, which is the Rn in a product with the dynamics F, plus the L was the running cost, and all this is to be minimized over the control set A for 0 less than t less than capital T, and subject to the terminal condition Vxt equal to capital. So this is, we have started with ODE, but we ended up with the PDE. So you may think that it is going to be a very complicated method, but apparently this is very amenable to numerical computations. And so it has been very successful in many of the approaches, but if you look at Ivan's Introduction to Optimal Control book, he has very simple examples of what is the value function. He has a very simple example of J. J is just modulus of X, and the particular case of U takes only 1 or 2 or 3 values. And then you can calculate by hand, like we did earlier, the maximum value of J. And that gives the value function, but it fails to be C1. So the point is, very often, it is not going to be C1. In some interval, it may be C1, but there may be transitions where it may fail to be C1. So here, the contribution of Pierre-Louis was the viscosity solution concept, which justifies that the value function is indeed a solution of the HJB equation in the sense of, in the viscosity solution sense. So that is the latest in this, but maybe I can stop here and come to the references. So this Brinquist and Tikhomirov also has optimization book, also has the inequality constraints when you get unique optimum, when you have several, all this, you may find theorems in that book also. Also in Donald Kirk, optimal control theory. Evans' Introduction to Mathematical Optimal Control, where I mentioned he has good examples of value function easily calculated by hand. Daniel Lieberson compares calculus of variations and optimal control, and he combines them. That's also a very interesting book to read. And I said more history in Tikhomirov, and Zabzik Mathematical Control Theory also has some information. Okay, so then we are done with lecture 2. I will move to lecture. So I have planned lecture 3 and 4 to be in PDE. So those of you who are not very comfortable with PDE concepts may find it a little technical, but what I wanted to say is it is the same kind of philosophy, like we started with one variable, several variables, and then infinite dimension, calculus of variations, optimal control. In all of them, we are finding some derivative and equating it to zero. And that gives me, and if you have constraints, you have Lagrange multipliers, you have an adjoint vector. So we saw in the earlier optimal control problem, we had an optimality system. X dot was the given dynamics, and we wrote down P dot was the what we found out from our Euler-Lagrange equation. And similar things will happen even in the PDE case, except that to justify all of them, we may have to use the PDE tools, which could be a little more technical. So let me start with, I have organized the contents like this: optimal control of PDE, and the PDE study plan. In here, what happens is we have to worry about well-postness of the PDE first. So that will take some technicalities, and then we have to prove the existence of optimal control. And here also there will be the notion of adjoint equation, and that will be the adjoint to the original PDE, and we can write down the optimality system. So you see the structure is very similar to what we did in the earlier cases, particularly in the optimal control of ODE. So it will be the similar structure, but with more technical details. So let's see one example to motivate. So in many practical problems, a differential equation describes the steady state or the evolution of the system. And often the problem may also involve some control parameters. So we would like to find the best possible control which maximizes a certain payoff criterion or cost functional. So we are, as usual, as before, we are interested in existence of optimal control, and how to characterize the optimal control, and how to calculate the optimal control. Can we compute it? These are all the major questions. So we'll start with the elliptic equations. So how does one optimal control problem arise for elliptic equation? Let us see an example. So in all the things, I'm going to take omega to be a domain in Rn with smooth boundary gamma. And in this case, for the elliptic equation, I could interpret Y to be an electrostatic potential and U to be a current density, or I could interpret Y to be the temperature distribution and U to be a thermal flux or a heating. So the Y is assumed to be the solution of PDE like this: minus Laplacian of Y plus Y equal to F. The notation here is Y depends on the variable X, and X is, yeah, just a minute. Now I need my pen. Y is depending on X, and F is also depending on X. The X is hidden, but it is there. So it is it's an equation post for X in omega. So it can be electrostatic potential or temperature distribution. So I have taken first dy by dn equal to the normal derivative on the boundary is given by u. So this corresponds to, so when I come to PDE, I could put the control either on the boundary or in the interior. So instead of F, I could also put the control in the interior. Then we call it interior control, or you can put it on the boundary, which is a boundary control. And we want to know whether the temperature Y can be steered as close to the desired temperature YD. So we have to minimize Y minus YD. These are all functions of X. X is varying in omega. So Y minus YD square. Usually we take the L2 norm. Now we also want to minimize the consumed energy. The consumed energy is the U, the control that you are applying on the boundary. Suppose you are heating on the boundary, then you want to minimize the heating. So I should also put integral over gamma of mod U square. So my control functional will be the sum of these two, and we would like to minimize these. This is corresponding to the boundary control. We could also talk of interior control. So I have written both here. So the J, the cost functional, is half. I have put a half just to make it easy to cancel when I differentiate. Remember, we will always be differentiating to find the optimal point. So half y minus yd square integrated over omega with respect to x, and lambda by 2 omega mod u square. So this is the control is applied everywhere or in a small subset in omega. So minus Laplacian of y equal to beta times u. Beta is some constant which is a given constant, and y is 0 on gamma. This we call interior control. You could ask, how do I minimize, and what is the optimal control u which will make j to be the minimum? Similarly, in the boundary control problem, the same functional, but now u is defined only on the boundary. So lambda by 2 integral over gamma mod u square. And now I want, 1 minute, something is coming up. Okay. Yeah, the alpha times u minus y. So in the boundary, what the dy by dn will correspond to the heat flux, what heat is transferred. So that could be what is, you put in alpha u through the control, and the dy by dn plus alpha y is equal to alpha u. This is one boundary control problem. So are there any questions before I proceed?
Yes. So latest one is why does you modified the functional in this particular way?
Which
Um,
functional?
I don't know.
Which
Perhaps.
functional? Maybe that
And
yeah,
he's also asking why we take L2 norm. Is there any specific reason to use this norm?
We all like L2 because it's Hilbert space. So it's easier to work in L2. So because I can go to, when I differentiate, I'll get inner product. And it's easier to deal with Hilbert spaces rather than Banach spaces. You could also take LP norms, but we end up with Banach spaces, and I mean, it could be more technically complicated. So to explain, I have chosen L2 now. That's all. Nothing special.
Okay, so he's replied the maximize functional in the interior problem.
Maximize in the interior problem. Yeah, in both the cases, y minus yd square is the same. Okay. But the control term in the interior control problem, u is defined in the interior, not on the boundary. So I have to integrate u in the interior only. So that is why I have taken integral over omega of u square. Whereas in the boundary control problem, u is defined only on the boundary. So I can only integrate it on the boundary. So it is the nature of the problem, or where you are defining your control. It depends, the functional depends on the domain of definition of the control. Okay. Yeah. So let us go on.
And
So,
there is one more from the
oh,
earlier.
yeah.
How do we solve Hamilton-Jacobi-Bellman equation? It doesn't look like an initial value problem.
No, it is a PDE. It is quite complicated to solve. That's why I said we can only verify that value function satisfies this. Unless, I mean, except for very simple cases, we are not going to solve the value function. Actually, since I don't know much about computation, why it is preferred or why was it introduced, I can't explain much. Apparently, it helps to compute the optimal control by solving that PDE numerically. That is what I understand, but I have not tested it, so I can't tell you exactly. Hmm? We are not solving that HJB equation at all by hand. It's impossible. But apparently you can discretize it and put it in the computer. It's amenable to solution. Like in the case of we saw KKT, KKT also, there are so many possibilities, but systematically you can feed it to the computer. You go on testing one possibility after another, and you will ultimately arrive at a solution. So in that way, it seems to be amenable to calculations by the machine. But we don't solve by hand. We don't know. It's not easy. It's, first of all, it's a PDE, a lot more complicated to solve than an ODE. ODE also, I know only linear or some few things we can solve, isn't it? So the solution is out of the, so that is not going to help us much. Yeah. Anything else?
No, just know something. Okay, how do we show the existence of solution to HJB equation?
Yeah. That is also, there is a theorem you can show under some condition. Yeah, I have not prepared that slide, but Evans does discuss when there exists a solution to this HJB equation. Yeah, it is possible, but becoming a PD topic, it's as usual technically more challenging. It's not straightforward. So I avoided that. That's all.
These are
Okay.
all. Yeah.
Yeah, that's all.
These are all the questions.
Okay, so we are almost 3. So I'll just see what is next and then stop. We can continue after the break. So these are the sample problems. So I wanted to explain first a finite dimensional example, and then this will set the stage. Whatever we are doing here, we will repeat the same thing in the infinite dimensional operators. So let us consider J to be a map from Rn cross Rm to R. Now, the J is a function of Y and U. Y is coming from Rn, U, the control, is coming from Rm. Now, my equation is Ay equal to Bu. So, A is a matrix, B is another matrix, U is the control vector, and Y is the solution. See, what we have done is instead of the PDE, I'm substituting it by a matrix equation. The idea is the matrix operators are all finite dimensional operators, and it is easier to understand or easier to calculate the derivative. And this same thing we will try to put in infinite dimensional operator when we are dealing with the Laplacian. Now my example is JYU is half y minus yd square plus lambda u square, where y is a Rn vector, yd is the given Rn vector, u is a Rm vector. Okay. So it's a simple finite dimensional example. The principle is we try to reduce the j to a function of u alone. So if I can write the solution as a function of u, then I would have written the functional capital J as a function of J as a function of U alone. I'll call it f of U. This will be easier for me to differentiate. How do we do that? If A is invertible, it's easy. Y is equal to A inverse of BU. So the solution operator becomes A inverse of B, and reduced cost functional will be a function of just one variable. I will minimize with respect to that one variable U. So in the example, it is half of SU minus YD square plus lambda U square. So what is F prime U? This is easy because it's a quadratic term, or I can write it as SU minus YD, inner product SU minus YD, and that will give me S transpose acting on SU minus YD plus lambda U acting on. So the calculation of the derivative is very easy. Now we can write down our theorem, optimality condition, very easily. If it is a, let us say U admissible controls is a convex set, U bar is the solution to the minimization problem. If F prime U, U minus U bar is greater than or equal to 0. This becomes a variational inequality if UAD is a convex subset. Otherwise, if it is the whole space, then F prime U becomes 0. So it is the case, interesting case.